Welcome back to Mechanics and Control of Robotic Manipulator. Last two classes we have seen what is trajectory and how to generate a trajectory using a cubic polynomial or fifth order polynomial or cycloidal motion or straight away simple straight line interpolation with parabolic blend. So this particular lecture we are going to see along with the manipulator, in the sense we are bringing some parameter of the manipulator. So for that we are actually like trying to talk something called the types of what you call trajectory generation scheme for robotic manipulator. In that we can see that there are two schemes are available. One is joint space scheme, other one is task space scheme. So this is what we are focusing in this particular lecture. We'll see how that goes. So I already said there are two main ways a robot trajectory is specified. We are specifically mentioning on manipulator. So this all actually like related to the manipulator case. So in that sense we can actually like call joint space or configuration space schemes. So where the time trajectory or time history of a single or multiple actuated joints. So whereas the task space or operational space, or some people call even Cartesian space schemes, so the time history of a position and or orientation of the end effector. So in the sense this is what we call end effector trajectory, this is we call joint space trajectory, or you can say joint position, velocity and acceleration. So in that sense we will first talk about the joint space scheme. Even the joint space scheme can be done two way. So one is actually like sequence, in the sense series actuated joint. For example, now this is a simple serial 2R manipulator. So first I rotate this, then I will rotate this. Okay. So in the sense I have another joint. Okay. So now you can see like this is theta 2f and this is theta 0, you can say 1f, and this is theta 0 10 and this is theta 20, right. So now from here to here I can do, first I rotate only first joint, so I will keep it this, then I will rotate the second joint, or I can actually like synchronously rotate one to another. So we'll see the first one. Okay, before that we can actually just see that what are the things are given to us when we talk about manipulator trajectory generation. The initial and final positions and velocities are specified to us. The acceleration is given or not according to the case. If the acceleration given to us, initial and final acceleration, then we have to go for higher order polynomial. But if it is not given, only these are given, then we can go for cubic polynomial. So we already know this. So sometime or most of the manipulator required what you call second derivative in order to make the force finite, or you can say force profile, or you can say torque profile, or the voltage which supposed to be given to the motor is required. Then people always go for the second derivative, which is nothing but the acceleration is continuous, which is given to us. So now in that sense, so we'll take one sample. So we assume that this is the 0 0 location, and I am going to fix one of the 2R serial manipulator in this way. So this is the initial joint position of link 1, okay, and link 2. In the sense joint 2, this is joint 1, and this is the end effector. Okay. So now this is given. So now what additionally given, the initial initial velocity and final velocity is supposed to be given, that we assume in this case 0. Okay. Similarly, we are trying to see what would be the final position and you can say velocity. Final velocities we assume 0, but this is the final position. So now what one can actually like see, so how to reach from here to here and how to reach from here to here. So I already said there is a two way. So one way you can directly, you can say synchronize. So where theta 1 of t and theta 2 of t can be synchronized, in the sense both link 1 and 2 will actually like follow the profile. So each segment and actually like maintain this. Okay. For example, this made in 4 second, so this equally it is actually like make it in a 4 segment. Okay. So like that it will go. So that is what we are actually trying to see as the first scheme. So in the sense the theta 1 and theta 2 I plot it, where this is the initial and this is the final. So what we are trying to do, we are trying to go as a straight line. Okay. So although we are going to follow a cubic polynomial, but we are trying to reach in a straight, you can say straight line interpolation. So this is what we call the first type of joint space scheme where it is synchronously moving. The other one, it is actually like go like this or goes like this. So we will take this as the first one is EC, where the first link or first joint rotate, the second joint rotate like that. So in the sense we take the same condition, okay. So these are the initial and final, but what we are trying to do, first we are rotate the joint one, okay. So what we are trying to do, first we rotate the joint one. So this one remains, so just rotate, you can see, right. So then we will rotate this, okay. So that is what we do. So in the sense this is the first segment and this is the second segment. So this is what we call sequence joint space scheme. The other one is synchronous joint space scheme. So usually most of the robotic manipulator community use the what you call synchronous one. The sequence one is actually like very common. For example, you take robot operating system with a gazebo, or you can say move it and all. So you can see like each joint would be actually like rotate, then the next joint rotate, like that it will be showing. In the sense it will show the sequence, is there any collision happening or not, those things all will try to understand. So this is what we call the joint space scheme. So when we come to the task space scheme, which is little you can say peculiar kind of thing. So what we can see, the joint space schemes are useful as long you are actually like using in a direct you call configuration space control. But you think about something like you have something like a seam tracking or probably a line following or a curve following and all. So you need to actually see how your end effector is following, right. In that sense, so you are actually like bound to follow what you call the task space trajectory. In the sense the end effector profile need to follow for a given path. So now this trajectory you need to generate in smooth enough, okay. So for that we are actually like coming back to the you can say end effector trajectory generation, which is nothing but we call motion of the end effector, the motion planning in terms of position and orientation of the end effector. So what that mean? So we are trying to use a task space scheme. Most of the people, motion planning means nothing but task space you can say generation or trajectory generation. This is what we people usually see. So there are certain constraints, that is what we are trying to address, but this is more natural because you can see realistic and try to see, because the robot operator or the robotic task always defined with the end effector. So then it is actually like more natural. For example, I want to pick this and place it here, which is very natural to follow this. But if I do the same thing through the inverse kinematics and try to make a joint space scheme, that is actually little you can say unrealizable one, okay. And further you can see it is very easier to visualize, see, realize, and even checking for obstacle, everything is easy if you talk about. That's why we say this is more close to motion planning. Further what happened, the difficulty in planning is exists, which is we call limitation, mainly on the orientation due to the representation issue. So the representation, you know, the alpha, beta, gamma, we call the roll, pitch, angle is not explicitly visible to us, right. So in the sense the representation is actually complex. In that sense the difficulty in orientational generation or trajectory is always difficult, okay. So further what you need to know, traditionally there are two important task paths we have to consider, so which is universally follow. One is linear interpolation, which I already shown, which is nothing but a straight line path. Even you want to go for a position tracking, so you have x decide, y decide and z decide need to be generate. You can just generate only one and then you can generate based on that into two other. That is what we are going to see in the next one. The circular arc is actually like for given three you can say position, we can make a arc and do it, which is not common and I am not addressing in this particular lecture. If anybody interested, we can discuss in the live session, okay. So in that sense we are going to what you call one important constraint, any path, whether it is actually like you call joint space trajectory or you can say task space trajectory, it should be twice differentiable, which is nothing but so C2 continuous, okay. So that is what we are actually like trying to say, in the sense the profile is smooth enough up to at least acceleration level. So that is what we are actually like trying to see. So in that case So we assume that the initial position, initial velocity, final position and final velocity are given for a straight line. In the sense the spatial position and velocities are given to us. So now we want to generate. We assume that accelerations are actually like not considered. So in that sense, the straight line path for 3D space we can generate in a simple straight line interpolation where the x of t is the only variable which you need to derive. Okay. So this x of t you can actually like generate either cubic polynomial or fifth order polynomial, all those things you can do it. Since here actually like only initial and final velocity and initial and final positions are given, so better we can do the cubic polynomial and then we can compute what you call y of t and x of you can say z of t. Further you can actually like ensure that since you are following this is continuous, so then obviously the y of t and z of t also continuous. So that is what we actually like see. So for understanding that, we can actually like take the same example which we have seen in the joint space trajectory. We can see that these are the two given position. So this is the initial position and this is the final position. The initial and final velocity we assume to be 0. So what we need to follow? So you need to actually like generate the trajectory which is on the straight line. Okay. So this is what we are trying to do. But if you generate this, what would be the joint space trajectory look like? So we just wanted to see. So for that I am taking this is the corresponding, so theta 10 and this is corresponding theta 20 and this is theta 1f and this is theta 2f. Okay. So now how look like? Earlier case it is a joint space trajectory which was I can actually show it in yellow. This is a joint space trajectory generation, but the task space trajectory generation something like this. Okay. So that is what you can actually see. So now this may end up with a few issues. Those issues we are actually like seeing. So this can actually like go outside what you call the workspace possibility, because this point may be inside workspace, this is actually like inside workspace, but the path can go outside workspace. This is one possibility. The other possibility is this path can actually, for example, this is the initial position and this is the final position. I make a straight line. So this zone may be a near singular case. In that sense, the joint acceleration would be infinite. Similarly, joint velocity would be infinite. In the sense, infinite joint torque is required to control that, which is not preferred. Similarly, the other way around, so you have two situation can happen. So for example, this is one position. Okay. So this is one of the manipulator position and the other position is actually just mirror image. So then if you are actually like making it, so it's supposed to come to the other path. So it goes like this, suddenly it has to come back. It is very difficult to follow that way. Okay. So in that sense, the swapping may actually like end up with you can say discontinuous velocity and acceleration. These all can happen. So that is what we are trying to see. For that we are just taking a small manipulator configuration where L2 is smaller than L1. We assume that both joint 1 and joint 2 can rotate 360-degree rotation. So in the sense the workspace would be look like this. Okay. So this is the workspace. So now we take 2 points. So one point is here. Okay. This is the initial point and this is the final point. So now what you can actually see, the path which is supposed to be generated in this way. Now what you can see, this segment is not trackable. Why? It is actually like outside the workspace. So here it cannot actually like maintain. In the sense it is not due to the joint limit restriction. It is due to the link or geometry restriction. Okay. So not joint angle restriction, it is just a physical geometry restriction. So in this sense, this is actually like not possible. So that is what we can say, that the task space trajectory can end up with, you can say, not reachable points. This is one, you can say, case can happen. The second case, what we are actually like see, even the better thing is, if I generate this in a joint space trajectory, still it is actually like possible to track. Okay. So this is actually like a joint space trajectory. So anyhow, we will see these all in simulation, which will give more insight. But right now we are actually trying to see what can be the cases. So in that case, this is possible if you do in a joint space trajectory. But what happened? This is not trackable in the task space. The same thing we can try to see. So now L1 and L2 are same, in the sense L1 equal to L2. Now what would be the workspace? Workspace is a simple, you can say, filled circle, right? So now we take the similar way. There are 2 points. I intentionally take this way. So now if I connect, you can see that it is coming near singular. So what singular? So where the theta 2 can be 0 or pi, right? So in this case, it can be go till actually like phi or very close to phi. In the sense, the Jacobian inverse can go to infinite, goes to infinite. So in the sense, you are joint space acceleration can go infinite, which is not possible. Okay. So this is another case which is not exactly the singular point, it is near singular point. Even some cases it can even pass through the singular point. For example, I take one point here, so you can see like it is passed through the you can say even the boundary. So in that sense, this can be again overcome with the joint space trajectory. So if you take a joint space, so still this is actually like so possible. Okay. So this is actually like possible from this point to this point. Okay. Only thing is, so you have this is theta 1 0 and this is actually like theta 2 0 and this is actually like theta 1 f and this is actually like theta 2 f. That is what you would be knowing it. Okay. So now we can actually see what would be the third case. So possibility of ending with other inverse kinematic solution. So very simple example, this is what the given condition. Okay. So initial and this is the final. You can see, you just make a line here, it's look like a mirror image, right? So in that sense, you can see like it's supposed to follow the straight line. This instant need to change over, right, for following the other path. If it is simply going this as a joint space trajectory, it is possible in the sense, so this solution, so this joint space solution is possible, okay, or if I give this configuration, it is still possible, but if I actually like give this kind of configuration, it is not possible. That's what says that, so it ending with other inverse kinematic solution, then also it is not possible. So then people can think about even the joint space. In this case, even the joint space trajectory is very close to a singular point, but probably this example I took it that way, but most of the cases this can be even still followed with joint space trajectory. So how we can do the joint space trajectory? So we can take this x naught and y naught and you use inverse kinematic solution and you can find theta 1 naught and theta 2 naught. Okay. Similarly, you take xf and yf and take the inverse kinematic and you can find theta 1f and theta 2f and use t0 to tf as the trajectory generation and then you can make the path. Okay. So that way you can actually like do it. So that is actually like better for making the task space trajectory. So far what we have seen, so we have seen so many what you call trajectory generation schemes and even the type of you can say trajectory generation possible in manipulator. One is joint space, even in joint space there are actually like 2 subclasses and in task space we have seen, even in the task space we have seen one specific interpolation method, which is straight line interpolation, which is universally followed. That's why we have seen that, and even if you follow that, what would be the issues? That issues we have actually like already seen. So in that case, the next lecture what one can expect, we'll see first how individual trajectory can be generated, that we will see in simulation. Then we will see how that individual trajectory can be ported in joint space scheme or you call task space scheme. That is what we are you can say focusing in upcoming lectures. Until then, see you, bye. See you then.